Okay, welcome ladies and gentlemen. Lesson 3 from our Unit 5. We are going to be looking at a lot of graphs today, and we're going to try to connect the graphs of f, f prime, and f double prime. So first derivatives and second derivatives are what we're going to be looking at today. And how can we graph a function knowing things about the derivatives? So let's go ahead first and look at the first derivative test. At some critical point, like the ones we've been dealing with lately, if the derivative changes sign from positive to negative, so the derivative is positive at one point in time and then negative on the other side of c, that means you have a local maximum at c. And that should make sense. That means the slope on the left was negative, and the slope on the right, or sorry, we're looking at positive here. The slope on the right was positive, left was positive, and the slope on the right was negative, and therefore that's a maximum value. And likewise, if the derivative changes sign from negative to positive at c, then it is a local minimum, and that should make sense as well because the function is going downhill because it's got a negative slope, and then it becomes positive slope, so that has to be a minimum value at c. And this goes right along with our last lesson where we were talking about looking for critical points, finding where the derivative is equal to 0 or where it is undefined. If the derivative does not change value or change signs at c, then f has no local extreme value at c, and that would be something along the lines of a cubic function. A cubic function does this. At this point, the slope actually becomes 0, or it could. And this is not a minimum or a maximum because the slope on the left, the derivative on the left is positive, and the derivative on the right is positive. All right, so these three things are pretty important for us as we continue forward here. If you have an endpoint on your function, say you were given an interval with a closed interval, if the derivative is less than 0 for all the values bigger than a, so all the numbers to the right, since that's a left endpoint, then f has a local maximum at a. Notice the parentheses coincide with each other. If f prime is greater than 0, then it's a minimum. So basically saying, if the derivative is negative on the right side of the endpoint, then that endpoint is a maximum, and that makes sense. The derivative is less than. Likewise, if you have a right endpoint and the derivative is less than 0 for x less than b, then f has a local minimum value at b. Continuing with the first derivative test, there's a lot of things we can determine from the first derivative. We can use sign charts to determine extreme values. This is just a helpful way to do things. What we need to do first is find the derivative. And find the critical points. So this is really 3 times x plus 2 and x minus 2. If you factored that, that means we can do a sign chart kind of like we did in pre-calculus, where we have the value of -2 and +2, and we need to figure out what's going on between or in these other intervals. We know that this makes f prime 0 at -2 and 0 at positive 2. If we were to plug in a number out here, so let's say -3, and we plug in 0 here and a 3 here, numbers that are in these intervals, we would notice that -3, if we plug that in, we're going to get a negative times a negative, which is a positive. So f prime is positive on the left of -2. At 0, you plug in 0, you get a negative value. So the derivative is negative between the two critical points. And if you plug in a 3, you get positive. So this particular function is positive here. This is f of x, by the way. The slope is positive, and then the slope is 0. That means for the function f of x, -2 is a maximum value. Then it's negative here and then positive here, so therefore this is going to be a minimum value using one of those last pages from before this page. Looking at the derivative changing from positive to negative, and then from negative to positive shows us what our min and what our max is going to be. All right, another thing in the graph that we've never talked about before is something called concavity. We have these things called concave up and concave down. And if I was to graph that cubic we were just kind of looking at, concave down would be from here to about here, where it's down. The cave is going downwards, I guess, if you want to think about it that way. And then concave up. So this is concave down. This is concave up. So it's opening up above the minimum, or opening below the maximum here. So if you have a differentiable function, it's concave up when y prime is increasing. So it's concave up if the derivative is increasing, and it's concave down when the derivative is decreasing, which actually tells us to use the second derivative, which is coming up. The only way I know when the derivative is increasing is to look at the derivative of the derivative. So we can use the second derivative to determine if it's concave up or concave down, and that's coming up here in just a moment. So if you have a twice differentiable function, means you can just take the derivative twice, like a quadratic or a cubic or a quartic. That's a lot of what we're going to be dealing with, because polynomials are pretty relatively easy functions to introduce this to. So if the first derivative is increasing, that means the second derivative is greater than 0. So it's concave up, where the second derivative is greater than 0. It's concave down, where the second derivative is less than 0. And what that helps us do, we can actually create graphs given information about the derivatives, the first derivative and the second derivative. Oh, I'm gonna skip something here just a second. Okay. If I wanted to determine the concavity on the interval from 3 to 10, all I have to do is go like this. I need to look at y prime, that's 2x. I look at y double prime, which is 2. 2 is positive, which means y double prime is always greater than 0, which means this function, y equals x squared, is concave up because the second derivative is positive for the entire interval from 3 to 10. But something that goes along with bigger functions like cubics is this idea where I kind of drew it in there earlier, kind of where does it change from concave down to concave up? It would be really helpful if we had a name for that. And we do. It's called the point of inflection. It's where the function changes from concave down to concave up, or the other way around. So it's a point on the curve where y double prime is positive on one side and negative on the other. It has a tangent line at that point, but it's where concavity changes. And what we really want to look at is when does y double prime equal to 0? Now we'll look at an example here in just a moment. But what I kind of want to look at before I go to the point of inflection and concavity stuff, I kind of want to look at this particular graph. These graphs will more than likely show up on an AP exam where you are given the graph and you have to be able to read this graph to determine everything you know about the original function. First of all, you need to read that this is not the graph of f of x, but rather the graph of f prime. So you need to understand that this is the derivative function, not the original function. So there's some things we can do. We can actually try to sketch a possible example of what the graph of f is going to look like. And here's what we can do. We can say this. This right here from -4 up until 2, the derivative is positive. It's above the x-axis, and therefore my function has to be going up. But something interesting happens here. The derivative is 0. However, because the derivative does not change signs and go negative, it actually is not a maximum value. It actually just levels off and then goes positive again. That's flat, by the way. It's not curved. Because here the derivative is still positive, and it's still positive, and it's still positive, and then right here, it changes from positive to negative. So as I'm graphing some sort of function, right here, it has to start going back downhill. Because now the derivative is negative, and negative, and negative, and negative, and negative, and negative, and negative. And then right here again, the derivative becomes 0, so I need a slope of 0, and it's going to end right there. So you've got some very key points that you must have in your possible graph of f of x. Now this is not the exact function f of x, but rather an example of what f of x could look like. All right, let's go ahead and look at some more stuff with the second derivative. If you have a derivative at some point that makes a 0, and f double prime at that same point is less than 0, then that point is your local maximum. Likewise, if you have a derivative and you got a point that makes the function, the derivative 0, and at that point for the second derivative is greater than 0, then f has a local minimum at x equals c. So on that same function that we dealt with before, we can look at f prime. F prime is 3x squared minus 12, which is equal to 3 times x plus 2 and x minus 2. So that means f prime of 2 is equal to 0. and f prime of negative 2 is equal to 0. And we want to figure out using just the second derivative without a sign chart. We can do it without a sign chart saying, okay, well, what's the second derivative? Oops. Second derivative is just 6x. F double prime of 2 is 12. And f double prime of negative 2 is negative 12. Which means 2, if we look at this, the derivative is 0 and the second derivative is positive. Then we should have a minimum value. But that's not what I should have because that's not what it was. Oh, yeah, it was. Never mind. I'm looking at these backwards. Okay, so also, because this derivative is 0 at negative 2 and negative at negative, the second derivative is negative at negative 2, then negative 2 is a maximum. Notice I didn't need a sign chart. Even though sign charts are legitimate items, for some reason they're not accepted as work on a free response question on the AP exam. So be careful when you use that when it comes to those last 6 questions. So if you were trying to graph the function f, and you're given things about f prime and f double prime, or even if you're given the graphs, here's what you need to do. You need to identify any extreme values, any minimums or maximums. Figure out where the intervals, or find the intervals that make the function increasing or decreasing. Find where the function is concave up or concave down with your inflection point. Find your inflection point as well. And sketch the possible graph of f. Now, I did put that graph probably in the wrong spot. But kind of follow along what I did on that graph back there. So if this is the function f, I can do a little bit of stuff here. F double prime is 12x squared minus 12x, or sorry, 24x. F prime of x can be rewritten as 4x squared times x minus 3. So that means f prime of 0 is equal to 0, and f prime of 3 is equal to 0. I'm just going to do a little bit of work here. 12x and x minus 2. That's not necessary, but it kind of might help me a little bit here. F prime or f double prime of 0 is equal to 0. And f double prime of 3 is equal to 1 times 36 is 36. So it's positive. Which means at x equals 0. There's all sorts of stuff we can figure out here, actually. At x equals 0, it's neither a minimum or a maximum. But at x equals 3, because my second derivative is positive, it's concave up. And at 3, it's a minimum value. So I do know at x equals 3, it's a minimum value here. And at x equals 0, I don't care where I draw it, really. If I'm trying to draw the function f, it doesn't matter where I draw it. I know it's going to be probably somewhat horizontal, and I know this is going to be a minimum. Oh, I guess I do need to figure this out. Between 0 and 3. Between 0 and 3, is the first derivative positive or negative? So let's go ahead and look at a really quick sign chart that I forgot to do here. If I go 0 and 3, if I plug in a 1, I get 1 and a negative, so it's negative. So the slope between these 2 points, between x equals 0 and x equals 3, has to be negative. Okay, so let's see if I can draw a better line here. So it has to be negative. This has to be a minimum value because when you plug in a 4, this becomes positive, so the slope is now positive on this side. This doesn't change signs, and you'll notice that when you plug in a negative 1 value, this also becomes negative. So this is going to kind of come up here like this, and here's a possible graph for f of x. I've used everything that I know. I know that the derivative is negative between negative infinity and 0, and between 0 and 3, so it's always going downhill until 3, and then it goes back uphill after 3. My inflection point was right there because f double prime of 0 was 0. It's kind of an inflection point, but we don't actually call it one. I know I said it, but this is not an inflection point because it doesn't change from concave up to concave down. It's actually all concave up. But there's an example of what we're going to be doing. Okay, so this particular lesson kind of throws people a little bit because you have to be able to look between 3 different things. You have to look from f to f prime to f double prime and really keep your mind wrapped around what you're trying to look for. All right, so that finishes off. I will see you guys tomorrow.